All right, so it's a pleasure today to have Marin Bukov with us. So Marin did his PhD at Boston University with Anatoly Polkovnikov, and after that he was a postdoc at UC Berkeley, Moore Fellow, and now he's starting his own group at in Bulgaria, Sofia University. So he works on all kinds of quantum dynamics problems, machine learning as well. And today he will tell us about pre-thermalization in Plateau systems. So Marin, please go ahead.
Thanks, Zlatko, for giving me the opportunity to present some of our ongoing study with Christoph Fleckenstein here. So I'll be speaking about Floquet pre-thermalization in many body systems away from the high frequency limit. So as I said, this is a joint work with Christoph, who recently graduated at the University of Würzburg and is now already moved to Stockholm to the group of Jens Barderson as a postdoc. So as you guys know, in the last, let's say 10 or maybe 20 years, there was a lot of interest in periodically driven systems. And in particular, this was solicited by experimental studies in all kinds of platforms. In ultra-cold atoms, people have realized topological states of matter and also artificial gauge fields with the help of periodic drives. But also in other platforms like photonic insulators, people have observed topological excitations. And not just quantum simulators, but also in quantum materials, people have used or applied periodic drives in order to engineer band dispersion. So with the help of a periodic modulation, high frequency periodic modulation, it turns out that you can open up non-trivial gaps in the dispersion relation. So this is all on the practical side, but periodically driven systems are also interested from fundamental perspective. And in particular, because they seem to live on the boundary between equilibrium and non-equilibrium physics. So I hope that this relation is going to become clear later on in the talk. But the basic idea is that Floquet systems are equilibrium-like in a sense because of a specific form of their time evolution operator. And at the same time, they're non-equilibrium-like because energy is not conserved and because they can exhibit phenomena that equilibrium systems cannot. And I wanted to say that thermalization and equilibration is also a problem that is interesting from an experimental perspective. And recently, there's been also experiments in cold atoms where people have observed exactly these phenomena in a system of interacting periodically driven bosons. Now, when we talk about thermalization, then we definitely need to define energy absorption and how that works in interacting quantum periodically driven systems. So I'd like to start right away with an example here for you. So consider a spin chain. This is a common chain that is used in quantum dynamics. So we have a time-dependent Hamiltonian, the time-dependent of which is separated in two parts. So there is an X part and a Z part defined here, which are applied in an alternating order in time. So that we have essentially a periodic system, a periodic Hamiltonian. And we would like to study under this application, under this time dependence, how energy conservation is broken and how the system eventually absorbs energy. So here I have defined the frequency of switching, right? So this sequence has a period of repetition, and then one can associate to that period a frequency of switching, capital omega. So whenever the frequency of switching is much larger than all the single particle energy scales, like the interaction energy scale or the external magnetic fields in the spin chain, then we expect that the behavior of the system will essentially be governed by the time average Hamiltonian. And the time average Hamiltonian in this model is just the sum of the two parts, the X and the Z parts. And so, if we want to study energy absorption, then the time average Hamiltonian is a first choice that then one can measure the energy of, right? And so what one can do is one could prepare the system in the ground state of that specific Hamiltonian, but then evolve it with the exact dynamics and observe how much energy is absorbed by the system as we increase time. So L here is just an integer that measures the number of driving cycles. So this is something that I also should mention. So typically in these periodically driven systems, people are interested in stroboscopic dynamics. That means that we are only interested in doing measurements at full integers of the driving period. And what you see here on the left is an example of such a simulation on a small chain of, say, 15 or 16 sites, where you can kind of see the curve of, the energy curve. So one interesting thing that you immediately should see here is that the system seems to be reluctant to absorb energy for quite a long time, on the order of say 1,000 driving cycles, and then afterwards it starts heating up gradually before it reaches this featureless infinite temperature state that I'm going to speak to in a second. So if you're wondering why this could happen, why we could have like such a slow absorption, then you should remember that we work in the regime, or we're interested in the regime of a high driving frequency, where the frequency, as I said, is much larger than all the single particle processes. And so what that means intuitively is that in order to absorb, one photon, if you wish, from the drive, or one quantum from the drive, you need a number of single particle processes, and this number is actually not small. And so it turns out that because of that, the amplitude for this process to occur is exponentially suppressed. So in fact, you can do some rigorous estimates on that people have done, and you can show that energy absorption is indeed exponentially suppressed in the driving frequency. And so that's a really, really interesting result, because in fact, it shows us that even though you might have a strongly interacting many-body system, for as long as you can avoid like direct resonances, which essentially is the equivalent to this condition, then you're guaranteed that your system is not going to absorb energy up to exponentially long times. And this is the starting point for these studies on Floquet engineering, and for using periodically driven periodic drives in order to ascribe non-trivial properties to certain systems. And so this is essentially also the reason for the formation of this long plateau here, which is known under the name of prethermal plateau, so prethermal window. Okay, now let's formalize this a little bit better. So let's try to understand how we can describe the physics of this plateau. Now, as I already mentioned, in Floquet systems, the fundamental object of interest is the unitary operator of one period, of one driving cycle, which is just defined here for our system of interest. It's just the consecutive application of two unitaries. And then, of course, because this is a unitary operator, then you can always represent it as the exponent of some Hermitian operator, HF, which is known as the Floquet Hamiltonian. The only problem is that it's actually hard to compute that object. So you know that you have this effective dynamics, which is why these periodically driven systems look like equilibrium systems, but they're not quite equilibrium systems, because this object here can be either local or non-local, depending on the properties of the drive. And so what people do in this case is they look at so-called inverse frequency expansion. So they say, well, maybe we don't know exactly the Floquet Hamiltonian, but we can compute an approximation to that Hamiltonian, which I label here by H effective, which, as we already anticipated, to leading order in the inverse frequency is given by the time average Hamiltonian. But then you can add inverse frequencies corrections to that. And then in that setup, one can try to understand now this curve here. And in particular, I'd like to draw your attention to 4 stages of thermalization in the high frequency regime. So first, there is a stage or a regime of constrained thermalization, where the system essentially thermalizes with respect to this effective Hamiltonian before it enters the prethermal plateau. Then in the prethermal plateau, the system is well captured by this effective Hamiltonian. But then eventually, if you wait long enough, the continuous exposition of the system to the drive eventually makes it realize that energy is not conserved. And then the system starts slowly heating up until, and enters a third regime, so-called unconstrained thermalization, before it eventually reaches the infinite temperature state, which is just a featureless state where the capacity of the system to absorb energy from the drive has been completely saturated. So one thing I would like to mention is that there are these 4 stages, but they're not sharp. These stages are essentially crossovers at all scales. But you could think of the dynamics in the stages 1 and 2 as a quench to this effective Hamiltonian, and then you can think of the dynamics in the other stages as a quench to this full Floquet Hamiltonian. And what I want you to appreciate here is that while in stage 1 and 2, or for the description of the dynamics in the stage 1 and 2, it's actually sufficient, to approximate the Floquet Hamiltonian by this effective Hamiltonian. Then this effective Hamiltonian does not actually capture the dynamics, the heating dynamics to infinite temperature. So it does not capture stages 3 and 4. And you can understand this intuitively in the following way. Well, we've said already that the heating should be exponentially suppressed. So it's exponential in the frequency. But then this function e to the minus omega is in fact a non-analytic function in the inverse frequency, right? So that's one of these prototypical examples of non-analytic functions. Therefore, it has essentially zero radius of convergence around frequency equals infinity. And because of that, the entire idea of performing a inverse frequency approximation is sort of doomed to fail. Now, this does not mean that this expansion is useless, but it simply tells us that the expansion does not capture the onset of unconstrained thermalization starting here in the beginning of stage 3. So that's something that's important to keep in mind.
Sorry, a quick question. What was the initial state for the dynamics that you have in this plot?
So the initial state here is the ground state of the average Hamiltonian, but in fact, this dynamic, this behavior does not depend much on the initial state. So you can start with initial states that are pure states. You can start with initial states that are even thermal states. You will still see the same behavior, close to the infinite frequency limit.
But if the initial state is indeed the ground state of the average Hamiltonian, and you're saying that in these regimes 1 and 2, the dynamics is well governed by the effective Hamiltonian, which is namely the average Hamiltonian again, why is there this discrepancy between the blue and red lines?
Right, because we are actually always at finite frequencies, so we're never exactly at infinite frequency. This is just a theoretical idealization. Even in experiments, you consider finite frequencies, and so there's always going to be some higher order correction terms that are eventually going to give you that difference here in energy.
So can I make a sharp statement that if I come up with a static Hamiltonian where I truncate the 1 over omega expansion to some finite orders, importantly, then I can actually make this red line go very close to the blue line?
That's correct, yes.
Okay.
That's correct. Well, you could make this red line come close to the blue line here in that regime, right? In stages 1 and 2.
Yes, yeah.
You're never going to be able to make the red line, follow or start increasing.
Yeah, no, sure, of course.
Yeah.
Okay, yeah, thanks.
Okay, great. Yeah, but so in the last part of this introduction, I just wanted to motivate, where this name pre-thermal plateau comes from. So, if we consider, just this pre-thermal plateau stage for a second, then, the eigenstate thermalization hypothesis tells us that if the effective Hamiltonian is a non-integrable Hamiltonian, that is to say, there's only an intensive number of conserved quantities, so we don't have an extensive number of integrals of motion. Then the system, the state of the system will thermalize locally with respect to that under that drive, and moreover, it will go to a thermal state with a temperature set by the energy density of the initial state. And so we can essentially associate a pre-thermal temperature here. At the same time, of course, we all know that if we wait long enough, then the system is doomed to go to the infinite temperature state. And so in that case, this is only a pre-thermal regime because the actual thermal regime happens at much later times. So this is just to motivate the name of why this is called a pre-thermal plateau. Okay. Now, this is the last part of the introduction. So I'd like to mention that none of this physics about pre-thermal plateaus and their periodic drives in many body systems has anything to do with quantum mechanics. So in fact, you can take a system of classical rotors. So these are just classical spin degrees of freedom. You can define the exact same dynamics with the same Hamiltonian. except here in that case, you can take a much bigger number of degrees of freedom. So you can consider like hundreds, if not thousands of spins. And then you can look at the energy absorption in that system. So here I have defined a quantity that's slightly different. So this quantity Q is nothing but a specifically renormalized energy absorption, so that when Q is equal to 0, then the system does not absorb energy at all. And whenever Q is equal to 1, then the system absorbs the maximum possible amount of energy. So this is just the renormalization of the curve. But what I wanted to stress here is that the exact same 4 stages of thermalization, so constrained thermalization, pre-thermal plateau, unconstrained thermalization, and then infinite temperature state, they are very clearly distinguishable in this completely classical Hamiltonian dynamics in that spin chain. So you know, this pre-thermalization physics is not necessarily something that that is quantum. Nonetheless, it's still interesting to investigate, you know, quantum regime and supplementary and look supplementary at the classical regime, which can provide us with slightly larger systems. Okay, so are there any questions so far?
Yeah, can I ask one? So for the classical thing you talked about here, is it like the condition is the condition for the applicability of the high frequency regime the same, namely that omega is larger than, you know, JH and G, for example?
Yes. I am talking about the high frequency regime, and indeed, you know, everything I've said so far happens at large frequencies. And now in the second part of the talk, I would like to show you one possible way of extending some of these physics to intermediate and low frequencies. How this could potentially work for specific class of systems.
And what about the bounds on the pre-thermal plateau? Are they the same in the quantum and classical, or?
That's what I was asking actually. If it's quantitatively related.
Yes, it is exponential. So you still have a, you know, an exponential a suppression of heating. In fact, the estimates, you know, the derivation is very close in both cases. So there is a paper, I think, by Takashi Mori that showed that one can rigorously derive an upper bound on the energy absorption, which is exponentially suppressed in the drive frequency. Maybe to give you like just an intuition of how you could think about it. So when we started this study, you know, one thing that I was thinking about that could give us like something different, you know, in the classical system is that the Hamilton equations of motion are actually nonlinear equations of motion, and whereas Schrodinger's equation is a linear equation. So I thought, you know, maybe because of that you might actually see something different. But it turns out that that's actually not the case, because, you know, when you compare Hamilton's equation of motion to Schrodinger's equation of motion, then you're like comparing apples and oranges. A much more proper comparison is to compare Schrodinger's equation to Liouville's equation for the phase space density. And Liouville's equation for the phase space density is a linear equation of motion, classically, which is now a periodically driven linear equation. And then it turns out that Fouquet theorem applies in the exact same way. And you can use essentially the same formalism, the same linear algebra formalism to show the bounds. I don't know if that gave you some intuition about why it's very similar. Okay. Any more questions here? Right. So then let me move to the topic of today. So today I'd like to introduce a class of periodically kicked many-body systems, you know, with the help of which I can try to extend this pre-thermal behavior to finite drive frequencies, so low, intermediate and low drive frequencies. So first I'll introduce that class, and then we'll do 2 examples. And the first example is just a non-integrable drive, where we just take the mixed field Ising model. And then we're going to look at, you know, I'll show you that there's a pre-thermal plateau, and then it occurs in the observables, entanglement, and, you know, pretty much all quantities you can come up with. Then we'll look at subsystem thermalization, we'll look at the heating rates, we'll look at the robustness of that model to drive, to noise in the period of the drive. And then hopefully there will be time for me to show you an integrable drive where we actually use an Ising model without quantum fluctuations to generate the dynamics. And this model is interesting because it'll actually allow us, unlike the previous one, it'll allow us to actually consider finite frequency corrections and then even derive like some expressions for some approximate descriptions, a description for the pre-thermal plateau. Okay. So here's, the idea. It's, I think, a very simple, if not a trivial idea. So we consider a class of unitaries which has the following form. So we have like 3 unitaries where there's, first a Hamiltonian H, and then there's a Hamiltonian V, and then there's another Hamiltonian H. So it's applied, like consecutively. So this defines a Fouquet unitary for the process, and then this process repeats over and over again. And the Hamiltonian H is an arbitrary object, an arbitrary matrix. But the Hamiltonian V, or the operator V, is constrained to have commensurate spectrum. So what does it mean to have a commensurate spectrum? It means that the energy gaps in the spectrum are essentially the same. So I'll give a more precise definition in a second. So H is arbitrary and V is commensurate, but H is almost arbitrary, not completely arbitrary, because the condition that I'd like to impose here is that the average Hamiltonian, which is just the sum of the two or proportional to the sum of the two, is a non-integrable object. And the reason why I'd like to have a non-integrable Hamiltonian is because I would like to make use of the power of the eigenstate thermalization hypothesis. I would like my dynamics to be thermalizing. And I'll study exactly how this thermalization occurs. Now, if you think that the condition on the commensurability of V is too restrictive, I'd just like to recall for you that all many-body interaction terms are essentially, well, let's say nearest neighbor many-body interaction terms, or local interaction terms, are essentially of density-density type. And the density-density operator has always a commensurate spectrum. However, in this talk, I will do something a little bit simpler. Namely, I'll consider another Hamiltonian which has commensurate spectrum, which is just the sum over all X Pauli matrices. So now, why is this commensurability structure interesting, or why is it important, and how is it actually defined? So first of all, I will call V commensurate if there exists some time or period, capital T, such that the exponentiated V, this part of the unitary, wraps up to the identity. And you can convince yourself that this is always the case for this Hamiltonian here, but you can also convince yourself that it's true, as I said, for all locally only interacting terms. And so because now we have such a structure, then you see what happens if I try to evaluate the Fouquet unitary at these commensurate points. If I evaluate at these commensurate points, then this middle term, this kick term, essentially vanishes, and so I'm left only with my Hamiltonian H. And so this construction, if we think of heating, here let's say some heating rate on the period axis, this construction essentially induces the existence of special points, commensurate points, T star, which are evenly spaced, defined by this equation here, where the system just is completely prevented from absorbing energy. So at these special points, there's absolutely no energy absorption whatsoever, and this is just a trivial fact by construction. What's not so trivial is to ask what is going on in the vicinity of those points. So we already know that the first of these points, k equals 0 point, is the 0 period or infinite frequency regime. And this is the regime that has been investigated a lot so far, and that's also the regime that we looked at in the introduction of this talk. And now what I'd like to do is I'd like to investigate what happens around some of these regimes, and why can these actually give us like some pre-thermal behavior? Well, because if you actually evaluate the Fouquet unitary, say some epsilon away from the from a commensurate point, then you see that in this kick term here, in the V term, the large part essentially disappears, and so what you end up having is a kicked system where there's like a large Hamiltonian H. I'm calling it a large term because its duration T is essentially large, followed by a small kick V. Last thing I want to mention here is that this construction of having an HVH is just here for convenience, and you could do the exact same thing by just having an H and V, so just two unitaries. It's gonna work in the exact same way. So let me just state the questions that I'd like to look at throughout the rest of the talk. So the first is, under what conditions can there exist a prethermal plateau in the vicinity of TK star? Are there any qualitative differences between the infinite frequency regime and the finite frequency regimes? Is there an effective analytical description, in the vicinity of that point, like similar to the high frequency expansion here? And does thermalization dynamic depends on whether H is integrable or non-integrable? So remember, H is a Hamiltonian that actually governs that. So that's the setup. Any questions about the setup? Okay. So the first system, as promised, that I'd like to look at is the non-integrable mixed field Ising model. So that's given here by that Hamiltonian. So notice that it contains all fields, the X and the Z field, and then additionally this commensurate term V, as I said, is always going to be fixed to be along the X-axis. So what I like is I'd like to initialize my system in some pure state. In this case, I just choose that to be a domain wall state, and then I generate dynamics with that kicked system. And what I'm interested in is looking at the time dependence of some observables. So here on the right, I'm showing you on the x-axis time. So this is just an integer multiple of the driving cycle. And then on the y-axis, I'm showing you either this energy, normalized energy absorption quantity, or the entanglement entropy of half the chain, where the system size here is 20. And the different colors correspond to different values of epsilon. Remember, epsilon is the deviation from this commensurate point. And so what you see here in the first curve, in the energy absorption curve, is that indeed the system remains, at the initial energy density until a few decades before it eventually starts heating up and it reaches infinite temperature. In fact, in the curves for the entanglement entropy, which are observable independent and know only about the evolved quantum state, you can see a very nice prethermal plateau forming. And indeed, this is a prethermal plateau that is long-lived, as seen here. So if you would like to look at like some subsystem, then you may as well check what happens with a local ZZ interaction term, where this observable first drops to that prethermal plateau value, and then eventually goes down to its infinite temperature value, which is 0, or the X magnetization, which also goes like into a plateau. So notice the initial state has no magnetization along the X direction because it's Z polarized. But then it turns out that like this effective Hamiltonian supports such an X magnetization, but it only supports it for a finite amount of time until the system exits the prethermal plateau. And then even the subsystem Hamiltonian shows a similar behavior. So the first message that I'd like you to take home today is that the prethermal plateau physics can in fact occur at low to intermediate drive frequencies in these lattice models. And indeed, these are low to intermediate frequencies because the actual frequency of switching, frequency of driving, goes down as the period goes up.
Sorry, what is this dashed line in, say, the entanglement entropy?
Yes, we'll come to that. Please hold your question for a couple of more slides. Any other questions here? Okay. Now that we've established,
Sorry, I have one small question. I mean, if you go back to the sort of definition of your commensurate operators, it sounds a bit like this sort of depends on the specifics of the Pauli algebra. I mean, yes, I mean, if you give me a sum of Pauli matrices, I can probably, because the square root of 1 and so on, I can probably find a time where
yes, but if you, for instance, take like fermions, interacting fermions, or
but that's also sigma z. I mean, that's also Pauli.
Yeah, but you can even, I think you can even take interacting bosons, and you could, I guess, still have a commensurate spectrum here, because the spectrum of
Yeah, you can have NJ, right? I mean,
yeah.
if you have a commensurate spectrum, this always works. I mean, but
yeah, for as long as you keep the prefactor here independent of I and J, so you don't consider a long-range interacting system or something like that, then you could get away from the Pauli algebra. I don't think the Pauli algebra is a necessary condition here.
Okay. Yeah. Thanks.
But I guess the obvious question is what happens if you slightly break. Okay, you're discussing what happens as you go slightly away from. As I change the, well, don't change the commensurability, but go slightly away from the commensurate period. Is it exactly the same as keeping that period and then changing a bit? I guess it is the same, but I'm asking you to make sure. If I change from them being all commensurate to adding, let's say, I take the energy levels or the plateaus, right? And I add a small random number to each, so I break the commensurability. I make them slightly wider, right? Each band.
I think it.
Do you know what will happen?
Because you could always write your operator as a commensurate operator plus something else, right? And then the commensurate operator should disappear under the commensurability condition, and here you would have this V tilde, this leftover term.
But that V tilde would not be the same as V. I guess that's.
It'll not be the same as V, but you know.
Do you have any sense of how worse?
Yeah. Okay. Yeah. I mean, I agree. It's a slightly different situation, but I think it will define a very, very similar problem. Because in the end, I don't really care what V is here, right? The only condition I think that I'm using is that the sum of H plus V is non-integrable. And if you actually start from an H which is non-integrable, then I think there's no way of making it integrable. Well, okay.
No, but I guess
fine tune.
I would have thought you are assuming something on the operator norm of V, but okay, I can ask you later when we're done, so I don't eat up your time, right?
Oh, that's fine. Okay, good. So now, now that we have established this prethermal plateau, I would like to look at exactly how thermal it is, right? So I'd like to extract, if possible, the temperature of my state in that plateau. But how would you extract the temperature there? Well, so on one hand, we have the eigenstate thermalization hypothesis that gives us a prediction for that temperature, right? So there will be a density matrix coming from the eigenstate thermalization hypothesis. And on the other hand, I would like to extract, numerically from the data, the temperature. So let me start, first by telling you how to extract the data numerically. So to do that, I would like to define the diagonal density matrix, or the diagonal ensemble. And whenever one has like Floquet systems, then the diagonal ensemble is simply given by the projection of the initial state and the Floquet states in the Floquet basis. So that's all very nice, but it has two major deficiencies. The first one is that it requires the knowledge of the Floquet states, right? And that's actually not possible when you have like large system sizes here, like 20. So you just can't diagonalize this unitary to get all the states. And the second problem is kind of related to experiments that you cannot really do measurements in the Floquet basis. These are like very, very complicated projectors, so you don't have them at your disposal. So this already tells you, especially the second argument, that maybe this is not like a completely physical way to think about the problem. But it turns out that there is a physical way to define this diagonal density matrix, and you do it like that. So you evolve your system here in the prethermal plateau. And then what you do is you record the state on consecutive stroboscopic times. And you can record the state, say, for m consecutive stroboscopic times within the prethermal plateau. And you can build this pure state density matrix and then average over this time series, if you wish, this ensemble of stroboscopic times. And if you do that, then this defines for you a density matrix. And it turns out that this is exactly the diagonal density matrix. But it's this time it's not given in the Floquet eigenbasis, but it's given in the computational basis. So it's even possible to compute it. Now, because we work with finite system sizes here in these simulations, we would like to reduce finite size effects, and I'm additionally going to take this this density matrix, and I'm going to trace out half of a little bit more than half of the chain in this case. I'm only going to leave a few spins there. And this is going to define the reduced diagonal density matrix on one side. So once again, to define the reduced diagonal density matrix, all I need is my data points. All I need is my state, involved in time. And now I'd like to compare this to a thermal density matrix as predicted by the eigenstate thermalization hypothesis. So what does ETH say? ETH says that if I have an initial state which has some initial energy density epsilon I, then in the prethermal plateau, my system will go into a thermal ensemble described here by this thermal density matrix with respect to this effective Hamiltonian, right? Restricted to the subsystem of interest. And so this equation here, right? If I now have this a thermal ensemble for the subsystem, I can also evaluate, the energy density of my subsystem, and this energy density has to match the energy density of the initial state if the dynamics of the effective Hamiltonian is quantum chaotic. That is to say, if the effective Hamiltonian is non-integrable. So this equation defines for me an implicit equation that I should solve to find the temperature of that state. So by solving this equation for beta, I essentially can construct another density matrix, this time a theory density matrix, if you wish, from the eigenstate thermalization hypothesis. And now I can compare the two density matrices, the one that the theory predicts to the one that I get from the dynamics. So what you see here on this plot is on the x-axis, I'm showing you the eigenenergies of this effective Hamiltonian, right? H effective on the subsystem. And on the y-axis, I'm showing you the spectrum of the two density matrices. And there's three kind of curves here. So first, there's the crosses, and the crosses just gives the data points. This is the numerical data obtained from the dynamics. And then to these crosses, I can just do a least square fit, which is given by the solid line, and that I can compare to the theoretical prediction that comes from solving this equation, which is shown as a dashed line here. Now the three different colors correspond to three different values of epsilon. Remember, epsilon is a deviation from the commensurate point. So if you do that, then you find a pretty good agreement, which essentially tells us that the state in the prethermal plateau is in fact a thermal state with respect to this effective Hamiltonian. So this is nothing surprising because the same thing is expected to happen close to the infinite frequency limit, and we see that it also happens here around these commensurate points. And another thing you could do is now you could take the slope of this curve, which on a semi-log plot is nothing but this exponent beta here, so nothing but the temperature. And what I'm interested in now is plotting the temperature as a function of the deviation away from the commensurate point. So what you see is that if epsilon is very big, then eventually my system reaches infinite temperature. So eventually temperature becomes beta becomes zero, right? Temperature becomes infinity, beta becomes zero. In the opposite extreme, where epsilon is very small and the prethermal plateau is very long-lived, then I find a value that is very close to this solid line here. This orange solid line is just a theoretical prediction for the temperature of the prethermal plateau. So this is all very nice, and in the middle there's an interpolation, and this interpolation has to be there, and the fact that it's there essentially is a manifestation of the fact that the exact Fouquet Hamiltonian is different from the effective Hamiltonian that we have computed. And you can convince yourself that you can keep adding more and more corrections to this guy, and you're never going to be able to capture this regime, just as we said, because there is a non-analyticity in the exact effective Hamiltonian, which is not present which cannot be captured by a Taylor expansion. So this is all, I'd say, not particularly exciting. But one thing that I found quite exciting was to see what happens now, just out of curiosity, if we take this equation, right, with the same effective Hamiltonian that we know that is not the exact Fouquet Hamiltonian, and we try to extract, a temperature at some energy density at a later point in time. So what this means is that, this is time here. So I start evolving my system, and I get into some intermediate time, L, right? And then, this defines for me some value for the energy density. And now I can use the exact same thermal ensemble, and I can check whether this thermal ensemble describes, well, the dynamics of the system or the state of the system at that stage. And indeed, that's the case here. So what you see here in that dashed line, so the dashed line is the temperature extracted from this equation, where you use still the inverse frequency Hamiltonian here, the effective Hamiltonian, but you supplement the left-hand side, or you upgrade the left-hand side to the instantaneous energy density. And that's already an interesting statement, because it tells us that the inverse frequency expansion, even though it could never capture the onset of heating, if you only take the static Hamiltonian and you add as an extra input the energy density, then this is enough to give a pretty good description to your state at any fixed point in time. The message here is that even after exiting the pre-thermal plateau, the state is still well described by a thermal ensemble with respect to the effective Hamiltonian. And the temperature is set by the instantaneous energy density.
Question.
Yes.
So is that enough to say it's thermal? I mean, it's so what you have this non-equilibrium state that's evolving, and you look at the energy as a function of time, and you're extracting a temperature as a function of time, effectively. Yeah, yes. Assuming that it's the average, you know, it's this thermal average.
Yes.
I would say that, you know, maybe, but shouldn't one check other things like FDT, for example?
I don't know. Like I think if I look at the eigenvalues of the reduced density matrix, and if I find a match in the eigenvalues of the reduced density matrix, then I would expect that fluctuation dissipation would follow from that right away. At least I don't see a reason why there's any more information in the quantum state that's not contained in the spectrum of the reduced density matrix.
Yeah, but here you're just looking at the average energy. As a function of time. Am I wrong on that?
So that's the average energy as a function of time, which I only use as an input to determine, you know, a temperature beta, right?
So couldn't I have a different?
And then wait, sorry, and then this gives me, you know, one theoretical prediction, right? That's essentially here this dashed line. Let's say this dashed line here, and then I compare the dashed line to the numerical data, which is the solid line, if you wish.
So let me ask a question about A. Are you plotting you probably said it, but so in A, you're plotting this. Is it that you're plotting the spectrum of the reduced density matrix?
It's the spectrum of the reduced density matrix on the semi-log Y scale.
Okay.
Yeah.
So this system is never far from equilibrium.
This system is never far from equilibrium. That's exactly the message. So the message is that at the moment the system enters the pre-thermal plateau, then it thermalizes there, and then afterwards it remains thermal with slowly, gradually changing temperature. Yes, and you could say, you know, well, but you know that would happen anyway. Well, there's still, you know, the possibility that the system, you know, is thermal in the pre-thermal plateau, then goes into another non-equilibrium state, and then eventually, you know, enters another thermal plateau at infinite temperature, right? But this essentially rules this scenario out. And what I think here is a non-trivial fact is that, you know, it's thermal, but when we say a thermal state, there's two ingredients, not just that we can define a temperature, but it's thermal with respect to some Hamiltonian. And at least to me, the non-trivial fact here is that we can essentially use the same Hamiltonian that we know is insufficient to capture the onset of thermalization, but it is sufficient to capture thermalization, you know, the thermostatic properties of the system.
I'm actually quite confused here. So in panel B, you have the instantaneous temperature, but this is at what time? Sorry.
The time is shown here, and I'm sorry to say that, but there was another plot here which I took out for time constraints, which essentially shows us that the agreement is also very nice if we vary the time duration.
So panel B is for a particular time.
Panel B is for a particular time, which is long, but we did the analysis for any of these intermediate times, and then we see a nice agreement also at intermediate times.
So okay, so the statement you're making is that you can keep the same effective Hamiltonian, which is the average Hamiltonian, and you just need to feed in the temperature of the time evolving state.
Yeah, or correspondingly via ETH the energy density.
Yeah, okay, it's the same thing.
Yeah, exactly.
And would the same statement be true if you, sorry, yeah, go ahead.
And one thing I just want to mention, right? So you keep the effective Hamiltonian, but then of course there's small deviation here, and then this deviation, you know, is due to the fact that I've ignored any corrections to that, right? So the idea is that if you keep increasing the corrections, then it's going to become a little bit better.
What if I take a slightly different H effective, which is not the average, but slightly different, which is also ergodic, which also satisfies CTH. I mean,
yeah, then you won't find a match of the two density matrices, right? So you know, in order to find a thermal state, it's not just enough, you know, to well, in order to find a thermal state, that the thermal state has two ingredients, right? One is the temperature, and the other one is the Hamiltonian. So when you say a thermal state, then you say thermal with respect to a specific Hamiltonian. And if you're thermal with respect to one Hamiltonian, you cannot be thermal with respect to another Hamiltonian, right?
Sure, but all I'm saying is that I can take a different ergodic time-independent Hamiltonian, and I get a different temperature. And I probably and why should the curve not look? Why should the two?
But then the comparison won't match, right? Because I'm comparing what comes from the eigenstate thermalization hypothesis to my dynamics, right? So part of this data here is purely dynamical. It does not know about this extracting beta and anything, right? So all the crosses are they come from this diagonal ensemble. They know nothing about this beta, right?
No, but okay.
And so if you want to have the same temperature, then you need to make sure that you're comparing, you know, the right objects.
No, but I mean, for instance, what if I just consider H effective to be H average plus the first Magnus expansion term? That's a different effective Hamiltonian, and it's probably a better match.
And yes, it is a better measure. That's correct. And unfortunately, I don't think I'm going to have time to get to that. But I could show you offline how that looks like afterwards.
Sure. Okay. Yeah.
And short message is, yes, it's a better measure. Yes, it works better. Yes, you can see that it becomes, you know, closer and closer.
Okay, yeah. So the average Hamiltonian is not special.
No, it's not special in any way.
Okay, yeah.
It just happens to be sufficient here because epsilon is also small. So the higher order corrections are not going to, you know, add much. Yeah.
Yeah. Thanks. Yeah.
Okay. So now let me move a little bit quicker now. So, you know, there was a question, what is this dashed line here? So we also would like to know about the heating rates, right? So we know that heating is exponentially suppressed close to infinite frequencies. Now we'd like to see whether this also holds here. And in order to do that, I'm going to define an empirical inverse heating rate, a gamma inverse, which is just the time it takes for the system to, you know, from the time it exits the pre-thermal plateau to reach half, you know, of the distance to the thermal plateau, right? So this dashed line is exactly half of the distance between the pre-thermal plateau and the thermal plateau. And at the moment this curve, you know, reaches, for example, that time, then I get my heating time. This is how I define it empirically. So if I do that, then I can, you know, plot the inverse heating rate as a function of epsilon. And if I do that on a log scale this time, then I find a straight line, which means that, you know, it's actually a power law. But not only a power law, it actually gives the exact exponent, almost the exact exponent, alpha equals almost 2, right? And that's, in fact, exactly what you would expect from Fermi's golden rule behavior. So this is something now that I'd like to emphasize. So in that specific system for this model, right, heating rates are not exponentially suppressed. Heating rates are power law suppressed, right? And because of that power law suppression, the values of epsilon cannot, you know, the values of epsilon I cannot take two big values of epsilon, because if my epsilon becomes too big, then eventually I start heating up right away without entering the pre-thermal plateau. So because of that, it was enough to take, you know, to consider small values of epsilon and consequently to ignore the higher order corrections. This was just a side remark. So interestingly, unlike, you know, the infinite frequency points here in this model, we find Fermi's golden rule behavior, so power law scaling to the heating rate. The same thing holds, you know, if you extract the heating rate from the entanglement entropy or one of the observables, and you get the pretty much the exact same exponent. So everything is nice and consistent. And so the last part of the study for this model is something, you know, peculiar that we noticed in these curves. So, you know, this model is completely non-integrable. It should be completely ergodic, right? And yet we see that there are some curves that, in fact, don't seem to not make it to the infinite temperature plateau. And of course, you know, this is most likely a finite size effect, and we did like some finite size scaling. We showed that, you know, the same curve would slowly shift upwards at a fixed, you know, if you increase the system size. But we actually started thinking, at this fixed system size, is there a way to actually, make the dynamic a little bit, to restore ergodicity into dynamics? And so one way to restore ergodicity, and in fact to show that this is not fully ergodic, is to add some small noise to the Hamiltonian duration. So I remind you that this was our Fouquet unitary. So now what I'd like to do is every period, I'm going to add a small perturbation to the large term h, right? So the duration of the large term is going to be shifted by a random number from a period to a period, and the strength of the short term of the kick I'm going to keep fixed. So now this defines a model that is no longer periodically driven, but is almost periodically driven if delta, the size of the noise, is small. And here is the result. What happens if you use a small noise size? Then you see that this curve here, which is marked by the dashed line, immediately goes up to infinite temperature. So even an infinitesimal noise is enough to restore ergodicity completely. I'm very happy to say that this essentially reduces finite size effects, because we were able to essentially simulate the dynamics of what would have happened if we had access to like 50 or 60 spins, which we can't do with the current methods. Another thing that's interesting when you add the noise here, so these are the rates as a function of epsilon for 3 different values of the noise. So the noise-free case is this blue curve. And the interesting thing is that the reason why these points are off the straight line that we just discussed is because because of this bending here, right? And what happens here is that at the moment you add some infinitesimal noise, then these points immediately go down, and not only that, but they align perfectly on the straight line. So what that means for us is that it doesn't matter how strong your noise is, right? Because the system is anyway ergodic. This is enough. Any value of the noise is enough to essentially reduce this non-ergodic effect and completely restore the ergodic dynamics. So that's a nice trick that we found along the way that I'd like to I wanted to share. Okay. Now let me go quickly in the last 6 minutes in the second part. So now what I'd like to do is I'd like to consider an Ising model without quantum fluctuations. So even though, this is like a weird name, an Ising model without quantum fluctuations, in fact, that's nothing but, everybody's favorite model. So the model where we alternate between the ZZ plus Z term and the X term. So that's the system that I started with at the very beginning of the talk. And because we've seen that, eventually the system goes to a prethermal plateau, and after that it remains thermal, then we decided that here, in this case, just again for numerical convenience, we will initialize the system right away from a thermal ensemble. So, we pick some finite value for beta, and then we start from a thermal ensemble with respect to this effective Hamiltonian. So if you now look at, in this case, the entanglement entropy as a function of time, for different values of epsilon, then you see again a prethermal plateau that emerges here. Except this time you see that the value of the prethermal plateau indeed depends on the value of epsilon. So as I vary epsilon, then the value of the prethermal plateau changes. And once again, this is not unexpected because there's also corrections to that term that have to be taken into account. That hopefully I'll have time to show you these in the end. But the really interesting thing that happens here in that system is that if you now look at the heating rates as a function of epsilon, you actually no longer find a power law, but you find an exponential of epsilon. So you could argue whether this is like a true exponential or a transient behavior, but we do see this behavior for at least 1.5 orders of magnitude, right? So at least there is a regime where the heating rate is well captured by an exponential. And so this is already kind of surprising because that's the same commensurate point that we were looking at in the non-integrable model, except this time we don't find power law rates, but we find a violation of Fermi's golden rule, and we find exponentially suppressed heating rates like in infinite frequency. Now, if you add the noise back to that model, right? So what I'm showing you here now is just the red curve, right? So that fixed value of epsilon, right? 0.25. But now I start adding the noise, then no matter how small of a noise you add to it, then eventually it will start deviating from the plateau, and then it will eventually reach the infinite temperature state. And whenever that happens for a finite, sufficiently large value of the noise, then the heating rates, as expected, also change, from an exponential in the noiseless case to a power law behavior in the noisy regime. The only difference here is that the exponent is no longer the one that comes from Fermi's golden rule. So this is kind of another surprise that we get in this model. So we seem to see like a completely expected completely Markovian dynamics, which is expected when we add the noise to the system. However, the exponent doesn't match Fermi's golden rule. So I'm currently thinking about how potentially to extract like that exponent, how to get like an idea of maybe not the exact number, but why it's not exactly 2, right? So why it's not Fermi's golden rule. So this basically comes to say that heating rates at these commensurate points can be either power law or exponentially suppressed, and that depends on the Hamiltonian that we use, right? That depends on this Hamiltonian H on the drive that we use, and it's currently not clear why in some models it's in some models Fouquet's Fermi's golden rule applies, and in other models it doesn't. But it's kind of suggestive that there might be like some refined estimates that one might be able to derive in this regime, so close to these commensurate points. Okay, so now the last thing that I'd like to show you is that for this model, another advantage or another reason for choosing this model is that it actually allows us to apply a variant of a high frequency expansion, which is called the replica expansion. So for this specific system here, you can think of the replica expansion as a resummation of a specific Baker-Campbell-Hausdorff subseries. So, I have this structure, then the Baker-Campbell-Hausdorff formula tells me how to essentially, reconcile the two exponents. And then if you imagine resumming a subseries, then this is something that is called the replica trick that was developed a couple of years ago. So you can do that, and indeed we did like this analysis. Then you can test, whether this in fact improves, right? And as was already suggested here, what we can do is we can do an experiment, just keeping the 0th order or maybe the 0th plus the 1st order, and then check whether this, improves our prediction. And so the first thing you could do is you could, start from the, from an eigenstate of the average Hamiltonian, and then evolve with the average Hamiltonian. Then of course nothing will happen in that case. But if you start from an eigenstate of the 0th Hamiltonian, then you evolve with the 0th plus the 1st correction, then you would already have some non-trivial value of the quench. So this is this constrained thermalization that I talked about in the very beginning. And then it settles down to a plateau. The interesting thing is, what we should be comparing this plateau to what will happen if you evolve with the exact dynamics, and that's the blue curve. And indeed, you see that the blue curve, is much closer to the green one than it is to the orange one. So I'm prone to believe that, if you even go to the 2nd order here, then you would find like another curve that would go like somewhere here. That's one, trivial check of this replica expansion. But we will also want you to do a check on the temperatures. So that's my last slide here. So what we do now is we go back to this, initial thermal state of the system, right? And now I have, I have 2 Hamiltonians, right? So I have either the 0th order or I have the 0th plus the 1st correction. So now I can define 2 initial thermal states, depending on which Hamiltonian I take. So the 2 curves essentially correspond to these 2 initial states, and this is their evolution if we measure always this best Hamiltonian that we have, which is the 0th plus the 1st correction. So now what you could imagine is you could imagine, doing the same procedure as before. So getting to the eigenvalues of the reduced density matrix, extracting the temperature. And when you extract the temperature, you have to do a fit. So you have to again decide whether you fit with respect to the 0th order or you fit with respect to the 1st order. So here's what you get. The data is the curve that you should be following. So the red line. Here's what you get if you fit with respect to the 0th order, right? And the green line is a theoretical prediction. Again, this is the one from the prethermal plateau. This is beta versus the time duration, and this is beta versus epsilon. So here's a plot where you could see actually what happens, as a function of time. So this is if you fit with respect to the 0th order. As you can see, there is some agreement, but there's actually quite a bit off. So now if you actually do the fitting with respect to the 1st order Hamiltonian, then you see a pretty good agreement. And this agreement is not only in time, but it's also agreement in epsilon. So in that case, I guess hopefully this answers, Roy's question from some time ago. Do you actually get, an improvement, of the description? Yes, you do get an improvement of the description, but you have to be able to compute the first correction. And it was not possible for us to compute the first correction for the non-integrable model, but it is possible to actually do that in this model. Okay, so here's a 4th message from today. So the inverse frequency expansion captures both the prethermal physics close to the commensurate points and the entire thermalization dynamics if you add as an input the energy density. Okay, so that brings me to the summary. So I'd like to go back to the 4 questions that I asked in the beginning of the talk. So the first one is, under what conditions can there exist a prethermal plateau in the vicinity of this star? Well, this is the exact same conditions as in the infinite frequency or close to the infinite frequency regime. So the drive frequency has to be fast compared to all single particle energy scales in the problem. There are indeed qualitative differences between the infinite frequency or the high frequency regime and these commensurate points. And the first one is that heating rates can be either power law or exponentially suppressed, and that depends on your actual drive. However, once that this is said, then all points that are greater than 0 actually behave the same. So we check what happens here, and then it's literally the same as what as the physics close to T2 and close to T3. So the T equals 0 is different, but the others are in fact similar. There is an effective analytical description in the vicinity, and it's given by the replica expansion, which captures the prethermal physics, and then it describes the state during the thermalizing dynamics. So not only during the prethermal plateau, but also outside of the prethermal plateau, if you allow for the extra input of the instantaneous energy density. And the last one is something that I did not have time to talk about, but in principle, it turns out that whether H is integrable or non-integrable is not the reason why we see, a difference in, for example, the heating rates. One other Hamiltonian that we checked, and which I don't have time for here, is the Transosiot-Ising model, which is an integrable Hamiltonian, again, right? But it has power law heating rates, and you can again see like the Fermi's golden rule applies to it. So somehow it looks like, the equilibrium description, integrable, non-integrable, does not transfer over to periodically driven systems. Okay, so with that, I'd like to post again the take-home messages, and I'd be happy to take any questions.
All right, thanks a lot. Since we ran a bit over time, do we have any pressing questions now?
I have one.
Go ahead.
So maybe too naive, but this exponential heating rate, that looks like Arrhenius law. So,
well,
is it a silly statement?
The thing is, the short answer is I don't know. I don't know because I'm not sure whether that's the same exponential as the exponential close to infinite frequencies. It could be just a different transient behavior. The problem comes from the fact that, at the available times that we have here, we can only do simulations for so long, and we can only do, that large system sizes. Then we are naturally cut off, right? So the fact that this, this curve here eventually gets cut off to the horizontal line is nothing but the fact that eventually I don't reach, my point here, right? So if the noise is too small and epsilon is too small, then I can't reach that threshold. So it's very hard, to get like definitive data. So whether it is Arrhenius law or not, at least I don't have like any evidence for that. Maybe it's, your intuition is right, but I don't have any evidence to substantiate that.
Okay, thanks.
Any other questions?
I think I'm still a bit confused about this first case where you added noise. Like what? Yeah, I can add noise, and then when L delta is order 1, things are clearly going to change. But what is this plateau before you add the noise? Still, I didn't really understand what it is.
So yes, so this is something that we're currently investigating. So we're not sure whether this is a complete plateau, because you can kind of see that it's not like stable, but it's definitely a manifestation. Like for some reason, this dynamics is not fully ergodic, right? And we don't know why. The reason why we know it's not fully ergodic is because we know that this one is, right? Because this one behaves exactly as expected. So most likely, this is a finite size effect. And it might, I don't have like open boundaries. I do have periodic boundaries, but maybe, somehow there's an excitation that propagates, like to the boundary, and then it starts going back, and there's some sort of interference effect that occurs, right? So this is one way that you could think about something that could give rise to that plateau. And then you make the system size larger and larger and larger, and then this effect eventually slowly disappears, right? However, you could only make the system size so large in these simulations, right? So unfortunately, methods like TBD or matrix product states don't allow you to capture this heating behavior for the very same reason as here. You're essentially creating a lot of entanglement. So this is not. I don't know of a good reliable method that allows us to reach longer system sizes. And so the question arises, how can we get the physics of large system sizes down to the small system sizes that we have access to? And one way of doing this is introducing this small noise, and that noise allows us to completely ergodize the dynamics. And notice that we don't lose anything, right? So, not even the heating rate changes, even if the noise varies by an order of magnitude, right? So in that problem, it's actually okay. In the other model, it turns out that, as I showed you, that the noise does change the physics. So when the noise is infinitesimal or 0, then you expect to see this exponential scaling of the heating rates. And when the noise becomes big enough, then this exponential goes in through a crossover to a power law. So there you have to be more careful.
Thank you.
Can you not check if that's a finite size effect by doing maybe 2 or 3 smaller sizes? I mean, you did 20.
We did do 2 or 3 smaller system sizes, and we did see that this thing shifts upwards, right? But even in the largest one, let me see if I can get this thing here from the appendix. So we're currently writing a paper, but it's not ready yet. Yeah, that's the one that you see here, right? So this is like this plateau, right? And then you kind of see if you increase the system size, then eventually it goes up, right?
Yeah.
But it's not as nice, right? The moment you add the noise, then you immediately destroy like that finite size dependence. So this is why it's like nice. And that's the same thing happens for the entanglement entropy, for the energy, or for the observable.
But isn't panel A of the top row just telling you that it really is a finite size effect, and one should not make a big deal of it?
As I said in the very beginning, it is a finite size effect, but it's still an interesting problem to understand. How can it be that even though you have one of the most ergodic Hamiltonians that you could think of, right? You could still have lack of ergodicity in your dynamics, right? Because having a system size of 16 or 18, there are a lot of states in the Hilbert space, right? So we're not talking.
I wouldn't call that Hamiltonian the most ergodic Hamiltonian of all.
Okay, yeah, we had this discussion, but here the parameters are chosen actually close to where this close to the most ergodic point. Let me put it that way. For that model, right?
All right, so maybe this is a good place to stop the recording, and then we can continue discussions. Thanks again.
Okay.